pretty sure I've got these slides posted. I tried to go through and condense topics onto individual slides, so now you've got everything that you would possibly need to use with sig figs. Remember, every single calculation you do, you're going to have to follow each of these steps. So you need to be able to identify the number of sig figs in each of your numbers. Then if you do some operation, addition, subtraction, or multiplication, division, you then have to translate those sig figs through to your answer. And then you might also have to bring in rounding as well. Okay, so be aware of that when you approach each of these problems. So everything on this slide must be memorized. Just because some people are very, very literal, which is fair, that does not mean you need to have the words memorized. The technique, okay, on how you approach each problem. I don't care necessarily about the sequence. All right? Oops. When we're measuring really big or really small numbers within a unit system, particularly within the metric system, that's where we bring in these symbols that allow us to scale larger or smaller than the base unit. And I can't remember if we talked about this or not, or if I did this morning. Each of these units, or the way this table is used, is how you would apply your conversion factor or generate your conversion factor. Okay? So if we have a terameter, the way this table works is that a terameter, 1 terameter, equals 10 to the 12th meters. So our power of 10 will always go in front of the base unit, not the one with the prefix. So if I wanted to convert centimeters, okay, we'd go through and say 1 centimeter is equal to 10 to the negative second meters. Notice the power of 10 goes in front of the meters. The one with the prefix, that always will carry the 1 in front of it. We'll look at a couple examples on this in a second because I noticed some big mistakes on the quiz. The next big issue is you may not see things that are only metric. We might have to deal with English metric conversions, and by might, you will. I will give you those conversions. The one piece of information that I won't tell you when I give you that information would be how many sig figs they carry. How many sig figs do your English metric conversions carry? 3. We'll assume 3, except for the inch to centimeters. The inch to centimeter conversion is exact. Okay, that has been redefined as 1 inch equaling exactly 2.54 centimeters. Okay, so before we push on, let's take a look at what was happening or what I noticed on the quiz for conversions. Okay, if we wanted to convert, say, I don't know, centimeters to meters. So let's say 3.2 centimeters, and I want you to convert that into meters. On the quiz, I did notice some really nice things. Number one, almost everybody was able to tell me what unit you were trying to get to, and you could also then tell me what you were starting with. Where I noticed some problems was looking at that conversion. Okay, and this is, again, positive in this case. I noticed that most people went through and aligned your units appropriately. Put the centimeters in the denominator and the meters in the numerator. Why? Well, it goes back to what we're trying to get. We want meters in our numerator in the answer, and we don't want centimeters, so they have to be arranged in this order to cancel out. Where the problem came in was bringing in the numbers. Okay? Can't tell you in how many cases I saw something along these lines. Okay? May not stand out as obvious in that case, so let's pick another case where it might stand out a little bit more obviously. Okay? One of the common ones that you had to convert was, say, seconds to minutes. Can you give me an equation that tells me what seconds to minutes are? What was that? So I don't want the unit factor yet. 60 seconds equals 1 minute. Okay. Why is that important? Well, what I ended up seeing was people arranging it. So let's say we wanted to get rid of seconds. and convert into minutes. Again, set up the units perfectly. Seconds needs to show up in the denominator. Minutes need to show up in the numerator. What was the next thing I saw? Okay, what happened? You remembered that the relationship is 60 and 1. You didn't put the numbers in right. So when we go, and that's exactly the problem that happened in this top case. So we want to set up the units to get us where we want. The next part of the problem is making sure you put the numbers in correctly. Okay, what do I mean? Well, what does this say? There are 60 minutes in 1 second. Really? Okay. It's a really simple, easy mistake to make. How can you fix or prevent that mistake? Well, look back to your equation. What number shows up in front of seconds? What number should show up in front of seconds when we move to the unit factor? 60. What number shows up in minutes in our equation? What number should show up in front of minutes in our unit factor? 1. Okay? That should clean up some of that number interpretation. So where I think this mistake is happening is you're rushing through it. In all fairness, you really had to rush on that last quiz. You had a lot of questions to pump through. Okay? So when it comes to the exam, slow down. Okay? Take your time on it. Most people don't like to do that because you need to finish. Everybody's got to finish it, got to finish it. Okay, let's say you go through and finish it, but you make this type of mistake on every question. What's your score? 0. Okay, now let's look at the converse. You slow down, you only answer one question. At the end of the exam, what's your score? 1. Which score is better? Okay? If you slow down and take your time but don't answer questions, okay, that is unfortunate. You didn't get those points. But you can at least guarantee that the ones that you did answer, you did right. Okay, so take the time, think about each of those steps as you approach it. Okay, which brings us back to this centimeter-meter issue. Okay, what we've been talking about in class is we could go back to our conversion and you would see that our conversion says centimeter, a whole bunch of space, and at the other end it says 10 to the minus 2. What did that mean off of our table? I think that was table 2.2. That says 1 centimeter equals 10 to the minus 2 meters. So again, go back to our conversion. Good job setting up the units right. What number should show up in front of centimeters? 1, because that's what our equation said. What number shows up in front of the meters? 10 to the negative 2. Okay? Now I'm going to go on a pseudo rant on this. The reason why I think a lot of you are making this mistake, okay, comes back to how you were trained in previous classes to deal with prefixes. Okay? And no offense to your other, well, sort of offense to your other teachers, they taught you a very backwards way that applied to one situation, only when you convert by powers of 10. Chemistry does more than convert by powers of 10. So those techniques that you learned on how to convert by powers of 10 and shift decimal places and shift all around, fantastic, that works. That applies to 2% of the problems that you're going to do in this class. Okay? What you need to understand is how we set up the unit factor so that we align those numbers in the correct locations. That requires a little bit more effort and work on your part, but as far as the effort and work, was it really that much more? Okay? You're looking at, yes, having to memorize that 10 to the negative 2 is our prefix for centi. Okay? But with that, you can now consistently do this conversion, and you can apply that method to every other conversion we're going to do this semester. Okay? So what I would recommend, if you had a previous class that allowed you to shift decimal places with these centi or powers of 10 conversions, use that information to your benefit to check your work. Okay, so when you go through and do the homework, set it up the way I'm describing now, this dimensional analysis way with these unit factors. Okay? Once you get an answer, go back and check it the old way, okay, the way that you should be fairly confident with. Okay? If your answers are the same, what does that mean? You just built some confidence in how to solve with dimensional analysis. That dimensional analysis skill will apply to everything else you do. Okay? So use your old methods to build your confidence with the material and how we need to solve it, and then you can advance and get better with the new technique. Okay? The new technique is really what's going to help you get through the class. I'm not going to grade on which technique you use. You can use whichever one you want. Just realize as soon as I ask something that's not a power of 10 and you don't know how to do this dimensional analysis setup, the likelihood that you put the numbers in incorrectly is 50-50. Okay? So the problem with that, you get 50% on the exam, you're not going to be particularly happy. Okay? So try and figure these out, set up those equations. Okay? Set up our unit factor, our equations that we've got at the bottom, and then apply that back to how these unit relationships show up. Okay? And always shift those numbers in. If you're going to use the table, so if you don't have some previous class messing with your head, if you're going to use that table, it gives you the prefix and the number. That number will always go in front of the base unit. What do I mean by the base unit? What are our base units? Okay. Meters is a good base unit. That's our base unit for what? Length. I've been calling it distance, but it's still length. What's another base unit? What was that? Liters, which we'll talk about today. That's our base unit for. What's another base unit? For mass. We have another one. We can bring in seconds. It's our base unit for time. Sometimes you'll see as S or even SEC. Okay, depending on how lazy that person happens to be. Okay? So when we're using that table and we slide prefixes in, that prefix number that you've got memorized always, always, always applies to the base unit. The other half of our conversion factor will be the one with the prefix in it. That one always gets the number 1 in front of it. Okay? Questions about that? Nothing? After all that angry talking? And no response, or I already scared you into asking questions?
Can you do a problem where you go from milliliters to liters?
Sure. I was thinking if I wanted to wait a little bit, but I can do that right now. So let's say you have 23.4 milliliters. What is the volume? People have been asking me to write out the question in liters. How do we set it up? First step. A equals eternal optimism. Units, liters. We started with 23.4 milliliters times now our conversion factor. Okay. We want to again evaluate, set up our units first, let the units attempt to solve the problem as much as possible for us. Okay, so let's compare starting material to, left to right. Does milliliters show up in our answer? No. So what has to happen to the milliliter unit? Okay, I need to have that in the denominator. Okay, do I have liter units in my starting or my Sorry, I'm getting into organic. In the left side. Okay, no. Some people are saying yes with that. Okay, it's not a yes. There aren't liters on the left-hand side. What do we have on the left-hand side? Milliliters. Different unit. Okay, so we need to get liters on top. Now we'd have to go back to our memorization and hope we memorize this appropriately. Okay, what does milli stand for? 10 to the negative third. I keep doing that too. You can see what method I've got memorized. Okay, it's 10 to the negative third. We said that power of 10 always applies to the base unit. Which one's our base unit? Liters. 10 to the negative third. What goes in front of the milliliters? 1. Now we crunch out our numbers or put it into our calculator and we'll get our answer. Okay. The other method some people may have memorized has to do with this exponent. A lot of people hate that negative exponent, and so we'll convert that into a different system. Because I don't want to get anybody confused with that, I'm not going to address that issue. Okay. But if you think that you're memorized a different relationship here, you can talk to me after class. We can talk about what's going on with that. It's ultimately the same technique or the same system. You just end up changing where your number falls. Okay, so it can be confusing for somebody that's dealing with it just from the get-go. Okay, so yep, you can use any method you want on the test short of looking at somebody else's paper. Or looking it up on the internet. Can't do that either. Other questions? Does that work for that?
Yes, thank you.
How do I do it? I put the parentheses around it, but it's doing it to the... How do I do it?
Can I talk to you after class about that? Okay. If you've got questions about how to get your calculator to work appropriately, talk to me after class. I can go through and make sure that we get that set up and you're comfortable with how to enter it. Particularly newer, fancier ones are probably going to take me a little bit of time to figure out exactly what they're trying to do. Okay. The older your calculator, the more likely I'll be able to tell you really fast what's going on with it. Okay. Do not wait to figure out how to use your calculator until the day of the exam. Okay, that's a really bad idea. Okay. Do the homework, get used to how to manipulate it so that when you get to the exam, you're comfortable with it. Okay? Other questions? Okay. What about all those English to metric units? How many of those do you have to memorize? None of them. Why not? Because I'm going to give them to you. Okay? I will give you all of the English to metric. The ones that you're responsible for memorizing are your prefixes, okay, your powers of 10 units. Percents, I think that's where we ended on Tuesday. What we're trying to do is just express different amounts to each other. Okay, and because I don't remember all the numbers, I'm not going to go into that path that I went through with this morning. All we're trying to do is come up with some way to relate two things to each other. Okay? It's typically by mass. The problems that you'll see on the exam, because I've already started to put it together, are all in the very similar format to the one we worked Tuesday, where we're looking at an alloy, and we mix two species together to make this alloy. What's the percent? Okay? Or how much of it is in a different sample. Okay? Should we go through another problem like that? Yes, it is. And I definitely have some calculators out, so you guys will definitely need to help me with some of this. We start with an alloy. We're going to say that alloy is made up of tin, doing the thing that you guys shouldn't be doing. The N needs to be lowercase. Tin and copper. Okay. In that alloy sample, our copper weighs 62.3 grams of copper, and let's say trying to do math in my head is a really bad idea, 7.6 grams of tin. Okay. What is the percent mass? Okay, percent by mass of copper in the alloy. So if we convert that question out, what we're asking is what is the mass of copper in the mass of the alloy I always forget this as well, times 100%, so that we can get our percent. Okay, do we know the mass of the copper? Yeah, what is it? 62.3 grams of copper. What's our total mass? Really, it's 79? Did I do that math wrong?
Yeah, you did. Yeah.
I was trying to make it even. So just 79?
79.9, so 78.
What did that make?
Wait, what was that number? 79.9. Wow, I made it that far off. Yeah, I did. 79.9. Should we worry about rounding? Okay, the not yet was a good point. Why do we not worry about rounding yet? We haven't finished the calculation. Okay, so now what do? Punch it into the calculator. What do we get as a number?
77.9.
77.9. Can you give me another one? Another digit?
2.
Okay, in theory, we get 77.972. Yes? Or no? Do we get a confirmation? Yeah, okay, so there we go. That ends up being our percent of copper in our alloy. Now we have to go through and evaluate are our sig figs. Okay, so where did our sig figs show up? Well, we've got two values that we ended up having to measure. How many sig figs in 62.3? How many sig figs in 79.9? Should it be 3? Why should it be 3? Where did the 79.9 come from?
Should be 80.
It was adding those two numbers. When we add these two numbers to each other, we're looking at new rules. So it's not just the number of sig figs, it's the least accurate position. Where's our least accurate position? The 10th place. So is our 79.9 an accurate value to report? Is that 9 in the 10th place? Yeah, so that is accurate. So we're okay calling that how many sig figs? 3. Okay, so how many sig figs should show up in our answer? 3. So we can go through and underline our 3 sig figs. 1, 2, 3. We now look at the next, or our first insignificant digit. What's its relationship to 5? It's bigger, which means we have to round up, and we get, why'd you say 78.0? We have to keep 3 sig figs. 98%. On the exam, some multiple choice answers, because that's always fun to address. Let's take a look at some multiple choice answers. I would probably have 77.972, was a reasonable one. 77.9, almost guaranteed I'll have a 78. And I'll have a 78.0, and because I'm tired of being creative, we got our 5th answer. Which of those is correct? The 78.0. Notice that almost all of those answers are very, very close to what your calculator spit out. You have to add that extra layer of interpretation to make sure that you get the correct answer. Does that make sense? Any questions about that? Okay. I am going to advance, but then kind of go backwards. Yeah, kind of go backwards. There's one more thing I wanted to talk about because I made the mistake while we were talking about in lecture. Remember we looked at a speed? Okay, remember all those speed conversions as we're shifting stuff around? Okay, what was the speed that we dealt with in this class? We had 45. We had 45 miles per hour, right? We said that was one way to write it. What was another way to write it? write it out as 45 miles per 1 hour. And this is where it got tricky. Okay? If we go through to evaluate the sig figs in this conversion factor, and I'm pretty sure I messed this up, at very least made it confusing. How many sig figs show up in that conversion?
2.
What's going on with that 1? Why'd you say 2? So I agree, 4 and 5 gives you 2 sig figs, absolutely. But that 1, you'd have to use the least, and that's 1. 1 has 1 sig fig. There's our answer. What was the measured value? 45 miles per hour. The measured value has already incorporated those sig figs. It's 45. We brought in the 1, or rather I brought in the 1 for what purpose? So that I can see that unit show up a little bit cleaner in the denominator. That 1 that I personally brought in is an exact 1. Which means that 1 does not impact the sig figs. And what we're looking at are 2 sig figs. Does that make sense? I just want to make sure we're extra clear on that because I definitely confused that and botched that in the lecture. Thank you. Appreciate the brutal honesty. Okay? So we can bring in that 1, but you have to remember that you personally brought it in, or that I personally brought it in. Okay? That's an artifact of our stuff. That's not going to affect our sig fig count. We have to go base our sig figs off of the measured value. The measured value in this case was the 45, not the 1. Okay?
Sorry, so it was a quiz because you didn't explain it well.
It's fair. I'll accept that.
What happens? Do you like?
So as far as how the quiz was graded, I graded the work. I didn't look at your answer. Yeah. So I only looked for the work and aligning where your units fell and that the numbers matched where the units should have been. Okay. Only in a few cases did I actually look at answers, and that's because there was such a mess of work there that I just hoped I could find an answer and said, okay, I agree with you, and just moved on. Okay. Other questions about that? Yes?
Along the lines of this problem here, the compound units, can you, I tried setting this up and I'm not getting it right. Can you do the problem where it says what is the speed in meters per second? And how do you do it?
You're clearly not the only one. Remember, I messed it up. So let's go back to an example. We had our motorcycle. Our motorcycle was traveling at 105 kilometers per hour. What is the speed in meters per second? Is that all you want, or do you want the time one too? How far in 120 seconds? Okay. So this is something I also noticed. A lot of people were confusing different calculations. Just because you've got some information doesn't mean you should use it. Make sure it's an appropriate time to use it. So if we go through and solve our first question, what is our speed in meters per second? So the first place to start equals meters per second. Next part, 105 kilometers per hour. Compare across. Notice that our units do not match in both circumstances, both in the numerator and the denominator. This means we have the freedom to pick whichever one we want to deal with first. We can then deal with the other one later. Because multiplication and division are communicative, we don't care about the order in which we do it. Several people want to break this problem up into 2 separate steps or 2 separate conversions. That's fine, but you can do it as one sweet long line. Okay, so where do you guys want to start?
Kilometers.
So we again evaluate, do we have kilometers in our answer? No. So where do the kilometers units have to be? Okay. What meter or what unit for distance do we have in our answer? So meters in our numerator. What's the relationship between those two? Is there a relationship first? Yes. Kili stands for 10 to the third, which applies to the meters, our base unit. We've now converted kilometers over to meters. Good job. So we now need to work on the next one. Do we? Yes.
How come the exponent was positive instead of negative?
Kili is a 10 to the third. Yeah, it just stands for what Kili is. It's a little bit odd because all of the negative ones are typically lowercase. Kili, for some reason, is lowercase and goes higher.
Okay, so this question, do we have to work with the powers of 10 or can we do 1,000?
You can do 1,000 as well. Yeah, if you want to multiply that out, don't have a problem with that. I'm trying to stick with the format that I remember from the book. Yep. Okay, so next part.
So, convert the hours.
So we need to get the hours. Okay, our hours are currently in our denominator. Do we have hours in our denominator for our answer? No, which means what has to happen? Our hours need to be put in the numerator so that they can cancel. Ideally, we want to go to seconds. I stop with the 3600 stuff. Is there a direct conversion between hours and seconds?
No.
Okay, most people don't have that memorized. So is there something in common between hours and seconds? Minutes. What's our relationship?
60 minutes and 1 hour.
60 minutes is 1 hour. Okay? Not a bad idea to say it out, too. So if you write it down and you wrote it the other way, you could say 60 hours is 1 minute. No, that didn't quite sound right. So it's probably the other way. Let's try that. 1 hour is 60 minutes. Oh, yeah, I like that. That makes sense. Okay? We fixed the hour issue, but what have we introduced at the same time? A minute issue. So now what do we have to do? We have to get rid of the minutes. I know that you want to bring in time or the numbers. I don't want to see numbers at this point. Okay? Ideally, we stick with our units first. Minutes, we're trying to get into seconds. What's the relationship? 1 minute, 60 seconds. Again, you could always say it out loud in your head on the exam. 1 minute equals 60 seconds. Yeah, okay, yeah, that makes sense. Or the other way, 60 minutes is 1 second. That doesn't quite sound right. Okay? If you get that kind of gut sinking feeling that something didn't feel right, probably a good idea to move on. Try a different problem and come back to it later. Maybe it'll settle in your brain and you'll be able to figure out what went wrong. Okay? You run that calculation and you get your answer in meters per second. Okay? This is what happens when you walk or pace. So, how many sig figs would we expect in our answer?
3.
Did you say 2 just for the heck of it? Oh, 60. Good call. I could see that. So let's take a look at our first. How many sig figs in that? Infinite. Are there 61 seconds in a minute? How about 60.1? No. There are exactly 60 seconds in exactly 1 minute, which means that conversion has infinite sig figs. What about the next one? Next one. Why is that one infinite? That it's within a metric system. Within systems, they're exact. It's only when you transfer between them. And then the last one, why 3 and not 1? The 1 was an artifact of me needing to see a number. Okay? So I put the 1, exactly 1 in there, so I didn't change the 105, which means my answer should be reported to 3 significant digits. Okay? Does that answer that one?
think what was throwing me off was I wasn't able to cancel because you had meters and hours, and I was like, wait a minute.
So that is something that's very, very common. People don't like jumping this. Okay? This hour can cancel with this hour, even though it's happening in the third step or second step. Why? Because multiplication is communicative. I can shift this over to here just as easily as where I've got it right now. If you don't like splitting it or running it in a line, do it as two separate calculations. First, convert it into meters per hour, then convert your meters per hour into meters per second. Okay, it's going to take a little bit longer, so you lose some efficiency in your writing, but it's not that bad. Yes?
And then just to get the far, like how far in 120 seconds, you just multiply by 120 seconds, right?
Okay, so for the sake of simplicity, let's say to solve that question, we were asking for how far in meters that we went. We've now got our conversion over into meters per second. Okay, so we can write a new problem. Okay, and I'm going to kind of leave up all of that work. What color did I saw that in? Yeah. Our new problem is we need equals meters. What information do we have? We have 120 seconds. Whoops. So if we want to incorporate it, and since I've been doing it, 120 seconds over 1, what's the unit? No, it's not no idea. You know exactly what that unit is. What is the unit of 1 in this case? It's nothing. There is no unit there. It's only there to hold the place and give us an idea of what's in the denominator. What's in the denominator? It is the only time that you can use a number without a unit. 1. Okay. Do we have a conversion that would get us to meters in our numerator, like our answer has, and get rid of seconds in our denominator? The answer from our previous problem. So we would take that number, slide it into here, multiply by 120. We now have the distance traveled in meters. Yes?
I know I'm like 2 minutes behind on this question, but you only count the sig things if it's like metric over English or English over metric. If it's like the same, if it's metric over metric or English over English, then it's infinite.
Yes.
Is that within one problem? If the entire problem deals with the metric system, then they're infinite? What if you're converting in, does that make sense?
If you're converting centimeters over into meters, the conversion factor is infinite.
There we go.
The number that you started with, that was a measurement.
Okay.
So the conversion will be infinite, but not the number, your measured value.
So the conversion rates that will be given if it's or memorized will be infinite.
Yeah.
So the top one will be 105,000 over 120, so I divide those to get my per second.
What's 60 times 60? You added. Don't add, it's multiply.
360.
But that now actually brings in where that 120 was coming from. A couple people wrote 120, and I was wondering where it came from. I was really confused. Yeah.
Yeah, I
So-
wondered why you wrote 120 up there, it's like, but I was just like, okay, he knows what he's doing.
Hi. Other questions? Okay. So volumes. Volumes are going to be a little bit more fun to deal with. Mathematically, we can look at the volume of a standard object. The easiest one to deal with would be a cube. We can look at length, width, and height. So if we multiply the length times the width times the height, we can get our volume. Hey, that looks like it went too far. Yep, it did. Okay, and that gives us our volume. Note that when we go through and actually report these, that the units on the length, width, and height should be the same. Okay. The textbook said must be, so we'll say must, but I'm pretty sure you can make up whatever units you want. It's just a weird volume measurement. It makes more sense to have them all come out the same. So if we tried to go through and figure out the length unit for this volume, what would it be? Well, what was the length of each side of the cube? 10 centimeters times its width times its height. 10 times 10 is 100 times 10, 1,000. So good, we got the number down. What's the unit? Centimeters cubed. Okay? That cube is going to come back and bite us in some problems, so you got to be careful with that. That cube just means we're multiplying centimeters times centimeters times centimeters. Okay? So that unit is a bit tedious to deal with because of the exponent. So we, being reasonable people, whenever we see something we don't like, what do? We invent something else. So what they came up with for our standard unit when it comes to volume is liters. What is a liter? It's a cube that measures 10 centimeters on a side. Okay, so it is defined as that exact volume. Okay, so that's your kind of conversion, if you will, between these. This comes in handy, and there's a reason they picked all these tens, and that reason comes from figuring out a metric conversion for something else. Can we convert centimeters cubed to a milliliter? I know you all are going, oh, 1 centimeter cubed is 1 milliliter. Don't do that. That's cheating. Don't do that yet. Let's derive that conversion factor. Where did that come from? Okay, so what do I mean by that? Well, we start with centimeters. Oh, come back here. How far away did it go? Oh, went really far. We start with our centimeters cubed. We want to end with milliliters. Okay, so our first attempt would be to say, do we have a relationship that can take centimeters cubed into milliliters?
1 centimeter cubed.
Not that one. Okay, no, we don't have that one, but we do know that if we take, according to our conversion factor up here, that if we take 1,000 centimeters cubed, we can convert it to a liter. Okay, so that's kind of nice. We've got a similarity between the two. Our common factor is our liters. Centimeters cubed can be converted over into liters. Can we convert liters now into milliliters? What's that? So, liters on the bottom, milliliters on top. What does milli mean? 10 to the negative 3. That power of 10 must show up in front of the base unit, which in this case is our liters. And the 1 shows up in front. Why bother to go through and do this? Well, let's pull out our conversion factor now and simplify that. What ends up happening? Take 1 divided by 1,000 times 1 divided by 10 to the negative 3. What do you get? You get 1 milliliter, 1 centimeter cubed. Okay. So when they went through and defined the liter as 10 centimeters cubed, they used it because we can also get 1 milliliter being 1 centimeter cubed. Or is 10 cubic centimeters. Sorry. One of the two. I keep swapping those units. Okay? So it's kind of a neat conversion to see those relationships. And you will be responsible for being able to measure a volume, both in the length measurements, so that's bringing in your meters, units, and also in your standard volume units, which would be your liters. Okay? So, questions? The reason this becomes tricky is when we start dealing with our length volume conversions, we have to be very, very careful that we don't get kind of sucked into a trap. And what do I mean by that? Well, let's take a square that measures a foot to a side. Okay, apparently this class isn't as up to date with their internet memes. Okay, so we've got 1 foot to each side. What's the area? How do we calculate area? Length times width, for a square at least. What's our length? 1 foot. What's our width? 1 foot. What do we get as an answer? Oh, geez, it's with that stupid square thing. Okay, I'm just going to write it. It's not ambiguous then. Okay, so that's what we end up with for our area with respect to feet. Okay, or rather feet squared. What happens if we now want to do this with respect to inches? So there's 2 ways that we can approach this. Whoops, shouldn't have erased that area formula, but you all got that, right? Okay. What is a foot? So we can say, right here, 12 inches, 12 inches. When I go to calculate my area, it'll be 12 inches times 12 inches, which gives us, careful, oh yeah, that's right, that stupid inch, yeah, we're just going to say that. There we go. Okay, so cool, that was pretty easy to go through. But we want something that's a little bit more manipulatable, okay? What if I wanted to convert not the area of a square, but the area of a triangle? Triangle wasn't that difficult. I meant star. Let's try a star. It's a little bit more difficult, okay? If we've got a star, that's not as easy to figure out the area. We'd have to go through and convert each side into all those appropriate dimensions. So what we want to do is come up with some way that we can incorporate those conversions in our calculation. Okay, so we started with, for our area, 1 foot squared. And what did we say that equaled? Or what did we want for our final answer? What units? Inches squared. Okay, and this is where the problem shows up. We go through, we put in our conversion factor, inches, feet. Right? What's the relationship between inches and feet? There are 12 inches and 1 foot. Most people go through and go, oh, feet. Whoop. First off, we take a look at that. Yeah, that didn't actually work, right? This is one of the reasons why our units can help us out. Feet times feet cubed or squared does not get rid of my feet unit. Okay, so go back and instead of trying to force it in, adjust with what you want. We want inches in our numerator, and we want feet in our denominator. Now what's our relationship? 12 inches, 1 foot. Okay. First common mistake, you say that your answer is 12 inches squared. Because, right, feet's in the numerator, feet's in the denominator. Oh, those totally cancel, don't they? No, the one in the denominator cancels our squared, doesn't cover the other foot. So how can we get rid of that other foot? We'll run our calculation again. Okay. Now, that will cancel the rest of it. And our answer becomes 144 inches squared, square inches. I've already got it backwards. Okay. The other common mistake. Okay, so let's erase that. Let's go back to our first attempt here. We look at it and say, okay, feet squared. Feet, well, it needs to be squared. I did see the squared, so let's go ahead and do it. That is feet squared, inches squared. Ta-da! Now it cancels. Still get 12. What's wrong? When we square, okay, if you're going to go through and do it in that method, you have to realize that that square applies to the number in front of it as well. Okay? So you either have to break out each of those conversions into individual steps so that you see that you're canceling each one, or you have to realize that that square must apply to everything in front of it. Okay, so you got to be really, really careful with that. Does that kind of make sense? Understand that? Good. Take a shot at it. I'll give you 5 minutes to do it. So we're starting with 498 centimeters cubed. But now it's my turn to talk. You will be responsible for density whether or not I talk about it. Centimeters cubed, we need to get over to inches cubed. So, same idea as we've been working with. We need some conversion factor that gets rid of centimeters and gives us inches. Do we have that relationship? 1 inch is 2.54 centimeters. If we track our units, okay, let's just look at the inches for the moment because that'll be the easiest. If we run this one calculation, what would our units as far as inches be in our numerator? Just inches. What did we want? We needed inches cubed. So we don't have enough inches in our answer at this point. So there's two approaches that we could go through. I'll go through the long one first. That means we need to do another conversion. What happened to our centimeters? Not quite. 1 centimeter turns in that 3 into a 2. So I would need a new conversion. I need to get rid of centimeters and get inches. Do I have a relationship between those? 1, 2.54. Getting closer, I'm now at inches squared, but that's still not quite right. And we also notice that centimeter will turn that last 2 into a 1. So I still haven't gotten rid of my centimeters appropriately. So do one more conversion, 1 inch, 2.54 centimeters. The other way to approach this, and a lot of people abbreviated it this way, and I'm just letting you know it is very common to make this mistake, is to go through and say this, 1 inch, 2.54 centimeters, and say again, oh, that just needs to be cubed, so cube and cube. Okay. That cube does not translate through to the 2.54 unless you remember it does. Okay, so you have to go through and translate or copy that through. So you could either make sure you bring in parentheses, okay, but even that can be a bit hazardous because that may show you good solid work, but does that mean you did that in your calculator? Okay, not necessarily. So be very careful when you approach these length volume comparisons or conversions because it is really easy to just do your conversion in between your English and metric, but then not translate the cubed or squared value that has to go along with it. Okay, so watch out for that. Be aware that it can happen, and it undoubtedly will show up on the exam. Okay? Did anybody actually calculate a number? What did you get for a number?
30.4.
Work that out a little bit further for me. 30 point.
Which sig figs out to 30.4.
So now we'd have to go through and evaluate our sig figs. How many sig figs and our conversion factors? Why 3? If it's 3, it's not exact. So I can accept 3, but your reasoning that you're going to say it's 3 is because it's an English to metric. I'll accept that, except, what's the but? They later came through and have now defined 1 inch as exactly 2.54 centimeters, which means it's not 3, it's infinite. Okay, so be aware of that. That's an extra little memorization thing. You'll notice in this problem it doesn't matter because how many sig figs do we have to start with? 3. So we can now go through and look at our final answer, underline our 3 digits. Our first insignificant digit, what's its relationship? Greater than 5, which means our answer becomes 30.4 inches cubed. I like the chorus of inches cubed, by the way. That was good. Questions on that? Okay. We can also look at the volume of an irregularly shaped object, or something that doesn't even have a real shape. So we could look at that goofy-looking star, or the crown. The crown's going to hold special significance in a second. Anybody recognize the crown? Just to be popular. Where did the crown come from? Hey, it's the Game of Thrones crown. Why not? And the last one, what are we trying to measure as far as the volume in that last image? Being a little bit inappropriate, I guess. I would have preferred to go with gas than your choice of words. It's an art exhibit somewhere. I don't know. It's a bull apparently headbutting some poor guy with the power of its methane. So if we wanted to figure out the volume of an irregularly shaped object or something that doesn't really carry a shape, like a gas, we can't just do this size dimensions things. We have to come up with another approach. So could we determine the volume in another method? Okay, it turns out we can. Archimedes, granted this is, again, Mike's history, but we're going to sort of trust it, was charged with the process of trying to figure out if a crown was indeed made entirely out of gold. So he had to come up with some way to non-destructively figure out information about it. That information he was trying to find was actually the density, which we'll talk about in a second. But there isn't an easy way to get that figured out if you can't figure out the volume. Okay? So what he went through and did, was happened to be thinking about it, allegedly, jumped in a tub, and when he sat in the tub to kind of soothe his thoughts and think about what happened, he noticed that the water level rose. So well, why did the water level rise? Thanks for the rise chorus, too. That makes me feel better. The water level rose proportionally to the amount of volume that he took up. So what he was able to discover is that we can measure a volume of an irregularly shaped object by taking a volume of water, throwing the object into it, and the volume is going to, or the water is going to displace by an equal amount of volume to the object. So that we don't have to actually do any weird calculations or figure out distances. We can just set it up by throwing it in some water. Nice and easy way to do it. So let's take a look at a quick example. If we were going to figure out the volume of the green jade sample, we take a look at what we started with initially and what we ended with after. And we look at our change in volume. Change is typically represented with a delta symbol. Volume will always be final minus initial. Our final volume was 60.5 milliliters minus our 50.0 milliliters. And we would get 10.5 milliliters. We now know the volume of the jade sample. Do we have the correct sig figs? How do we determine it? What was that? Sorry. That was weird. Not the lowest amount of sig figs. Maybe you change your phrasing, I might accept that. We don't look at the number of sig figs in this case. The least accurate value. What's our least position in this case? The 10th place. So when we report our answer, we need to report out to that 10th place. Okay, why do we change it? It's a different operation. Addition and subtraction follow the least accurate measurement. Multiplication and division are the number of them. Okay, so be aware that your rules do change a little bit when you apply these. Okay? We could also go through and look at it for measuring gas. So your textbook has this image, which is kind of neat. What we could do is heat a sample of some species in that test tube. There are plenty of compounds that, when they are heated, will decompose and release a gas. That gas can then pass through this elaborate system of tubing and now start to increase the pressure on that liquid. It's like it's adding its volume. The liquid then wants to displace away from it. The only way it can displace is by going up the tubing and out the other end. So what we can do is actually monitor the volume change either in our round bottom container, which is not easy to do, or we can measure it. What are you guys doing? I'll stand over here. We can look at the volume increase to determine how much gas was actually produced as the volume. I do want to add that we need to be very, very careful with this experimental design. Okay, why? What happens if we take a balloon and you heat it? What happens to the balloon? Before it pops, It expands. When we heat something, the volume will change. So when they set up this experiment, we have to be careful that the volume is changing based solely on the gas being added to the system, not the heat. How do we do that? We have to make sure that that flame is very far away from where our volume change is being measured, so that we can assume that when the gas actually hits the reaction, it's at room temperature, or at the temperature of the rest of the system. Okay? We will talk about that relationship, I think, later in the semester. You're looking at the ideal gas law. We won't worry about that now, though. Okay? Last thing that we wanted to get through would be density. There are some questions that we could actually work that are in these slides, but I don't think we're going to get to those. I'm just going to kind of talk through it, make sure we get it covered. It's an intrinsic property, so it's a characteristic of that individual species. So if we go through and try and look at some potential ways to compare these, let's think about which weighs more, pound of lead or pound of feathers, commonly asked of little kids. The little kid goes, oh, the pound of lead, pound of lead. What's the answer? They're the same. They both weigh a pound. And then you can point and laugh at the little kid. Ha, you got it wrong. You do that, right? No. Okay, well. I do it to not my kids. So the other way that you could perceive this is potentially along the lines of which would you rather be hit by? Well, the pound of feathers, we think about our feathers are nice and spread out. So when we get hit with the pound of feathers, it's really not that bad. But let's say we took those feathers and we condensed them down to occupy the same volume as the lead. That's going to hurt just as much. Okay? So it's one of our external applications that we're actually interpreting something else with this. It turns out it's a lot more complicated than what I'm discussing here. But what we're kind of comparing or thinking about is the density. It's the way our mass and volume are related for an individual species. The density is defined as the mass divided by the volume. So what unit, let's not do that, because that's on the next slide. So what we effectively have generated with the density is a new conversion factor. I can now relate mass into volume, assuming I know the density of the species that I'm working with. Okay? That density will change depending on the compound, so we can't always use the same calculation. Make sense? Okay. So what units do we associate with our density? Okay, so that's an interesting question. It's just mass and volume. What's a unit for mass? Grams. Unit for volume? Liters, milliliters. There are other units for grams? Or sorry, for mass? Yeah. We could go through with grams per milliliter, grams per liter, milligrams per liter, kilograms per liter. We get a ton of different options for our possible units. Which one do we actually decide to use? It's going to depend on the species. If we take a look at our solids and liquids, particularly ice and water, if we look at those numbers, relatively close to the same. Ice happens to come in at 0.917 grams per centimeter cubed, also known as a milliliter. Water, 1 gram per milliliter. What happens when we move to water vapor or a gas? Now we write that out. It's not just a gram per milliliter. Nice easy numbers. Now I have to write 0.000736 grams per milliliter. God, that's an awful lot of zeros. I wish there was a way that I could change those zeros into a letter. Say like a Greek prefix. I could now change my interpretation and bring it into milligrams or kilograms depending on the species, or change the volumes. So depending on what you're looking at, you might see the densities in different units. The ones that we typically work with, or at least that I've commonly worked with, are grams per milliliter. All right, that's your standard range for liquids. So possible values. Table's got your book's got a nice table. Table's got a nice book, right? Your book's got a nice table that goes through and summarizes a bunch of different densities for different species. So we now need to come up with some way to interpret those. And that's where we can shift to this diagram. So what is happening in this case? If we drop a block of, a rock. There's a rock. We throw it in some water. What happens? Sinks to the bottom. Why?
Because it's more dense than the water.
Has to do with density. It sinks to the bottom because it's more dense. So we could go through and now look at how different species separate with respect to each other, and that is looking at our density. So if we looked at our individual liquids, for instance, if you took oil and vinegar and we put them together, what happens? We see two layers, and we see the oil on top, the vinegar on the bottom. What does that mean? The vinegar was more dense than the oil. So the bigger our density, the larger our density, we'll talk about that briefly in a second too. Larger density sinks. So if we tried to go through and rank our densities for our liquid, water, and L2, which one is the most dense? L2 is a bigger number than our density for water, which is a bigger number, I keep doing I's, than liquid 1. Okay? And that's why we see that ordering. What happens if we shift to the blocks now? So now the blocks get a little bit more interesting. What can you tell me, about the density of, let's do block S2.
Not as dense as S3.
Okay, so we could compare it to the solids, but is it interacting with the solids? No. So let's look at how it's interacting with the liquids. We could go back and rank it back to the solids. It's not a bad idea. But I want to look at the liquids first.
So it's more dense than liquid 2.
If it's more dense than liquid 2, what does that mean?
No, it's, I'm sorry, it's less dense than liquid 2.
It's got to be less dense than liquid 2,
Yeah.
because that's why it's on top of liquid 2.
More dense than liquid 1.
More dense than liquid 1, but it's not interacting with liquid 1. So what's its relationship to water?
It's more dense than
It is more dense than water. How do you know it's not the same? It's at the bottom of the water as opposed to being somewhere in the middle, okay, which is a little bit trickier to deal with. If they have equal densities, would it sink? No. So you could put that species into the water, let go of it, and what's it going to do? It's going to stay right there. There's no reason for it to shift. Okay? What we're also looking at in this case is, or can look at in this case, is something known as specific gravity. Specific gravity, specific gravity, the SG is in reference to, I appreciate the better too, is in reference to something. What's our standard solvent that's used probably over 70-80% of the planet? Water. So when we're looking at a specific gravity, it is typically in reference to water. So we compare its density to water. So if we have a number that, or a specific gravity that's bigger than 1, what do we say? Species is more dense than water. What if it's less than 1? Less dense than water. What if it's equal to 1? Has the same density as water. Where does this become important? Since you mentioned specific gravity, maybe you know.
Yeah, it's measuring the alcohol to beer I used to brew.
Alcohol content is typically measured based on gravities. You can measure the sugar content before it ferments and the sugar content or the gravity after it ferments. Sugar will change the density of the solution as well as the alcohol. Okay? That can be compared and turned into a percent alcohol for that species, for that beer. So that's kind of fun to deal with. And you can make some good stuff too. Those were some problems. I think that was the end of it, yeah. So at the end of that, we've got some problems on dealing with densities. I'll leave you guys to look through those. I'll probably try and solve some and post a video as well so you can see some problems. Density is on the exam. The material that is not on the exam would be temperature and heat. Okay? So sorry for those of you in lab because I didn't get to temperature and heat. You will have to do some calculations with those in lab today.